We're going to look at velocity time graphs today and figuring out an object's displacement given some select amount of time. So our objective will be determine the change in position of an object based on the VT graph, the velocity time graph. This is standard 4 in the constant velocity unit. To illustrate this skill, I'm going to use 3 different models: a sketch, the mathematical model, and then finally the graph model, which will capture our objective. So let's consider an example. We have a penguin here, and the penguin top speed moves about 8 miles per hour swimming underwater. So here's my penguin swimming in that direction, 8 miles per hour. So after 1 hour passes, we know that the penguin has moved 8 miles. After another hour passes, now at 2 hours, the penguin has gone 16 miles. At 3 hours, 24 miles, and 4 hours, 32 miles. So based on the motion dot diagram, I know the change in position is 32 miles forward. So if I use, and this is just stating that, in 4 hours, the penguin has changed its position by positive 32 miles. Now I could also look at the mathematical analysis, and here I'm just paying close attention to the units. Now, this is the velocity of the penguin, 8 miles per hour. The unit that I want to end up with is just miles. I notice that there's an hour on the bottom, or on the denominator, so I am going to try and cancel this out. The way I'm going to cancel that out is by multiplying by hours on the numerator. So if I care about how far the penguin has gone in 4 hours, I should multiply by 4 hours so that I have hours on the numerator, hours on the denominator. These hours cancel out, and what I'm left with is 8 times 4, and the unit that's left over is miles. So 8 times 4 is 32. It's positive, so 32 miles. Unit analysis is going to be very advantageous if you are keen on using units in your mathematical equations. I highly recommend it. All right, so it covers 32 miles. We knew that. We're just verifying with the mathematical approach. And finally, the graphical approach. We're going to track the velocity of the penguin over time. As each hour passes, we're plotting on the y-axis its velocity. Well, the velocity doesn't change, notice. So here's the blue line is representing at hour 1. The velocity of the penguin is 8 miles per hour. At hour 2, still 8. Hour 3, still 8. So this is a constant horizontal line. On the y-axis, I have velocity. On the x-axis, I have time. Now, for some of you, this will be your first exposure to calculus. Dun, dun, dun. And what I will, and this is just a hand-waving calculus, but what we're going to consider is the area underneath the graph. That tells us something very important. Notice here, if I look at the area underneath the graph from 0 to 4 hours, 4 is on the length side of this rectangle, 8 is on the width, going from 0 to 8. So the area in here is 4 times 8, that's 32. That's the same as multiplying this value here, 8 miles per hour times 4 hours gives us 32 miles. Miles is what's left over. So if I find the area underneath the velocity time graph, I find the displacement. 4 on the length. I guess I'm calling this the width. 4 on the width, 8 on the length. Multiplying those two together gives me 32 miles. So the penguin has moved forward 32 miles. If this curve or if this graph was below the 0 line, so if it was negative 8 instead, that would just mean that the penguin is moving in the opposite direction. And if the penguin was moving at negative 8 miles per hour for 4 hours, the penguin would have moved backward 32 miles. Big point here, though, is that the area underneath the velocity time graph is the displacement, the change in position of the object. So long.